Hello everyone. So in this pre-lecture tutorial, we're going to start to review our material for Chapter 12. And Chapter 12 deals with solutions. And so we have briefly discussed solutions before at the beginning of the school year when we first started classifying matter between pure substances and mixtures. And so basically, if you recall, solutions are mixtures, but not only are they mixtures, they are what we call homogeneous mixtures. Meaning, again, if we review the meaning of homogeneous, basically that means that the solution or the mixture behaves and looks the same throughout. In other words, we don't see layers, we don't see solid particles, we don't see gas bubbles. Basically, we just see one mixture with one uniform color, and it all behaves uniformly. Now, essentially, now that we're going to talk in greater detail about solutions, we have to become acquainted with the parts of a solution. And so a solution usually is comprised of two types of parts. There's what we call the solute, right? And the solute is that component of the solution that is present in the lesser amount. And we have the solvent. And the solvent is generally that component of the solution that is present in the larger amount. And so basically, when you combine the two together, then you have your solution. Now, in this particular instance, our solute happens to be a solid. We can see the crystals, and the solvent is a liquid. It's water. Okay, and again, if we take a look at the substance we get in return, basically we have a solution with water as the solvent, or what we call an aqueous solution, which we usually denote with the symbol AQ in parentheses. Now, even though in this particular example we have a solid solute and a liquid solvent, it doesn't have to be that way. In class, we'll discuss in greater detail the different types of solutions that we can have, but it's entirely possible to have a liquid solute combined with a liquid solvent. It's entirely possible to have a gas solute combined with a liquid solvent. It's possible to have one gas be a solute and another gas be a solvent. It's entirely possible for a solid to be a solute combined with a solid solvent as well. And so we'll discuss this in greater detail in class. But I wanted to spend the bulk of this pre-lecture discussing how it is exactly that solutes, particularly solid solutes, actually become incorporated into the solvent to form the solution. And so basically that involves understanding the difference between dissociation and dissolution. Now, typically these terms can sometimes be confused with one another, and so it's important to distinguish between them. And so the first thing that you should be aware of is that ionic compounds dissociate. And what it means to dissociate, it means that these ionic compounds break down into the component ions present within the ionic compound. And so in this particular figure, basically they're showing you water molecules. These water molecules are red and white, and the hydrogen's white, the oxygen is red. And if you notice, they're a little bit bent over. Basically, we have hydrogens sticking out on one side of the oxygen. And so because of this bent over structure for water, basically one end of the water molecule has a bit of a positive charge and the other end has a bit of a negative charge. And so what that does is it gives water the ability to interact with things that might have a bit of a positive charge or a negative charge as well. And if you remember, ions are positively charged and negatively charged. And so if we take a look at this portion of the picture right here, if you notice, the oxygens are all attracted to this ion that's colored in green. And so basically, since we know the oxygen is the negatively charged part of the water molecule, we can infer, since again we know how positive charges and negative charges interact with each other. We know that positives and negatives attract. That means that this green sphere must be the model for a positive ion. Now, if you notice, the water molecules are surrounding it and sort of carrying it away from the rest of the solid ionic structure that's present at the bottom of the picture. Now, if we take a look at this region of the picture, notice what's going on here. Basically, these blue spheres happen to be attracting the hydrogen atoms associated with the water molecule, which we know those are the positive ends of the water molecules. And so that means that we can infer that these blue spheres are negative ions. And once again, the same thing will happen. Enough water molecules will surround these negative ions and carry them away from the solid structure. And so as a result, basically, as these ions are pulled away from the solid structure, eventually the solid structure falls apart and these ions are free. They're in aqueous solution. And so the ionic structure breaks down and everything dissociates and we get the solution. Now, covalent compounds do not have the same behavior. If you recall, ionic compounds involve a metal and a nonmetal. Okay, but covalent compounds basically are comprised completely of nonmetals. And so basically what we have here, this is actually a model for glucose, which if you recall has the formula C6H12O6. Now, if you notice, basically the way it works is each of these black spheres, those are carbons. But again, since we know that glucose also has hydrogen and oxygen, again, the white spheres are hydrogen and the red spheres are oxygen. And once again, basically water with its sort of bent over structure will actually start to surround the entire glucose molecule and be attracted to those portions of the glucose molecule that might have positive and negative charges. So for example, right here, here's a hydrogen atom on this particular water molecule. Notice that it gets attracted to the oxygen present here in glucose. And so because of that attraction, that water molecule will start to actually approach this particular oxygen atom in glucose. Notice that another water molecule experiences the same attraction throughout the entire molecule. Basically, you get more and more of those attractions occurring. And essentially what starts to happen is within the solid glucose, where you have basically multiple units of this glucose molecule, these water molecules will surround the whole thing and carry it away from the solid structure. But notice that the glucose molecule does not break apart. Basically, the water molecules surround the glucose molecule in its entirety. And so for that reason, we don't say that the glucose molecule dissociates, because if you remember, again, dissociation means breaking down into component parts or component ions. But we do say that the glucose dissolves. And so the reason why it's important to understand that difference is oftentimes we will actually go and we will use chemical equations to actually demonstrate either dissolution or dissociation. So for example, suppose I had sodium chloride, okay, as a solid, and I'm going to go ahead and put it in water. Again, since we have a metal, sodium, and a non-metal, chlorine, we know this compound is more than likely ionic, and so it should break apart into its component ions if I put it in water. And those ions should be the sodium cation and the chloride anion. And so each of these would then be an aqueous solution. Okay, now this is a rather simple example. It's entirely possible. Suppose that I have something like, say, potassium sulfide, okay, as a solid, and I put it in water. Okay, again, still, potassium is a metal, and sulfur is a non-metal. And so I'll still get the component ions back again. Basically, I still get potassium cation with a +1 charge, and in this instance, I'll get the sulfide ion with a 2- charge. But notice that if I'm writing a chemical equation, basically, I have to make sure the equation balances. And right now it doesn't because I had 2 potassiums on this side, but I only have 1 on that side. And so that means I have to insert a coefficient of 2 here. Notice that when I do that, on this side of the equation, on the left-hand side, notice that since this is a compound, compounds are neutral. And so the charge here on the left-hand side of the equation would be 0, since it's only the solid potassium sulfide that's present in the left-hand side of the reaction equation, or in this case, the dissociation equation. But on this side, I had 2 ions. Now, if the charge is 0 on this side, I have to make sure that the charge is 0 on the other side as well. By inserting this coefficient of 2, 2 times +1 would be +2. Notice that I have a 2- charge, that would be -2. If I add these charges together, I get the charge of 0 that I'm expecting. So what about if I had something like aluminum chloride? And I have that as a solid, and I go ahead and put that in water. Well, basically that would give me aluminum ions with a 3+ charge and chloride ions. But again, I have to make sure that the equation balances both by mass and by charge. And so I have 3 chlorines here, which means I have to insert a coefficient of 3 there. Notice again, my charge here should be 0 because I have a neutral compound on the left-hand side of the equation. Here, I have a 3 positive charge for aluminum, so that's +3. And now by inserting that coefficient of 3, now I have -3 as the aggregate charge for the chloride ion. So if I add those two together, I'll get 0 as I was expecting. Now, what about for those compounds that are covalent? For example, I mentioned glucose. All right, if I have solid glucose and I go ahead and I put that in water, can I show that I have an aqueous solution of glucose? Absolutely. But I shouldn't expect ions on the other side of the equation because, again, as we've discussed, there are no ions in covalent compounds. And we've also talked about the difference between dissociation and dissolution, and we know that this glucose molecule stays together. And so the way that we would represent that is simply by repeating the formula and simply putting the AQ abbreviation to show that we're discussing an aqueous solution of glucose. I'll give you another example of a covalent compound. This compound right here is methanol. And again, notice there are no metals present within the formula, and so it's more than likely that this is a covalent compound, and methanol is a liquid at room temperature, a pure liquid. I can go and I can put methanol in water, and basically I'll still get that attraction between water molecules and regions of the methanol molecule to create an aqueous solution. But once again, I shouldn't expect ions since this is a covalent compound. And so as a result, I would just repeat the formula and write in the aqueous symbol within the parentheses. So go ahead and respond to the follow-up questions associated with this pre-lecture tutorial. When we return to class, we'll discuss the material in greater detail. If you have any questions, feel free to email or bring up your questions in class. Okay, have a good night.